Hi guys, so yeah, we're going to try and talk about neutrinos. Now, out of interest, how many people have heard of neutrinos? Okay, this is good, this is a good start. How many people are here to try and learn about neutrinos? Okay, that's all good as well, that's perfect. And how many people are in the wrong room? Let's just see. No, believe me, I've had someone sit through half a talk for and then leave and realize he was in the wrong place. No, so neutrinos have recently been talked about in the media, and I think this is great because as a particle physicist myself, everyone's been talking about the Higgs boson and the God particle and everything like this. My field's kind of been lesser and kind of a little bit forgotten. And I'm not really surprised because neutrinos aren't amazingly exciting. They're not as sexy, I guess, as the Higgs boson. But believe it or not, they're absolutely everywhere around us. So as a particle physicist, I'm interested in finding out what the fundamental building blocks of nature are. And whether it's in the Large Hadron Collider by smashing things together to see what they fragment into, or whether it's by looking at the more subtle things like nuclear decay, in which the neutrino was discovered, we're still trying to find out what these blocks are, how they work, and how they interplay with each other. So we're very interested in fundamental forces as well. So not only finding out what these blocks are, but how the laws of nature tell them to interact with each other. Because it was from these raw building blocks in just the first few seconds after the universe, and quite a basic set of fundamental laws, fundamental forces, that everything around us, obviously it took billions of years, but everything around us kind of assembled itself together and to form us and everything around us right now. So with neutrinos, as I say, they're absolutely everywhere. Right now, even though the sun's down below the horizon, there are hundreds of billions coming from the sun, from nuclear reactions within the sun, and they're passing through us right now, about a couple of 100 billion every single second. But neutrinos, despite being so abundant, are hardly ever seen. In fact, they were only seen for the first time in 1956, and there's a very good reason for this. You've got electrons, which I hope you've all heard of. They have electric charge, and the good thing about the electromagnetic force is it's infinite in range. Okay, and this is you can see because of the light that's raining down on us now, and that's just electromagnetic force carriers kind of bouncing off the wall and back into your eyes, off me and into your eyes. So the electromagnetic force has an infinite range, and so it can influence lots of stuff, and in fact we use that influence to measure these charged particles. But the neutrino only interacts by something called the weak nuclear force. And the weak nuclear force is exactly as it says, extremely weak. But not only that, it's only got a range within the very center of an atom, within a nucleus. Okay? And most of the stuff around us is pretty much all empty space, 99.9999% pretty much empty space. But again, the reason it feels solid is because of this electromagnetic force, because that has a much larger range, and in fact it's the electrons in the atoms in my finger that are stopping my finger going through this wooden post, nothing but that force. If we were to get the weak nuclear force interacting, we'd have to come in as close as we can to we'd have to hit the nucleus square on. So we'd have to hit that 0.0001% if we were actually going to get any chance at all of a neutrino interacting, and even then it's still a roll of the dice as to whether they might interact. So these things are pretty ghostly. I mean, they are rarely seen, and in fact I think it was Beth and Perel's, a couple of scientists took the mathematics that Enrico Fermi and Wolfgang Pauli, the guys that were very much involved in the Manhattan Project and developing the nuclear bomb, they took the mathematics and they tried to calculate how often you would see a neutrino interacting with stuff around us. And they actually wrote in their paper that there's no practically possible way of seeing it. Okay? And this is true, but what you can look for is you can look for these charged particles, electrons and heavier versions of electrons being created through this interaction with the weak force. And so what we look for in our detectors is absolutely nothing coming in, but we see these charged particles being created as if by magic from nothing. And this is a signature of a neutrino. Okay, so nothing coming in and then an electron or heavier versions being created. Now I'm talking about these heavier versions. For some reason, nature has given us 3 sets of almost identical building blocks. The only difference is they're just heavier. So the electron itself has two heavier versions. We're not very imaginative, we just chose Greek letters. We chose the muon and the tau for these heavier versions, so they're just, again, getting fatter. And for these three different types of electron, there's three different types of neutrino. And what's interesting about a neutrino is, when you create them as one particular type, they don't live like that forever. They change their personality. So they can be created as an electron type, and we can measure them some distance later, and they've changed their mind, and they decide to create, say, a muon, a heavier version. And this is very interesting. This is quantum mechanics being shown on macroscopic scales. So quantum mechanics is the theory we have of our universe at the very small, and it's very bizarre because it's probabilistic. It's not deterministic. So deterministic would be something like mechanics. If you kicked a ball with a certain force in a certain direction, you could be pretty sure with my football skills I'd miss the goal. Okay, but in quantum mechanics, in the very small universe, it's all about probability. You can give something certain properties and give it, if you like, a kick in a certain direction, but there's no guaranteeing that those properties will stay the same, because it ceases to be a definite thing, becomes nothing but a ball of probability, and then at a later point it's told it has to make a decision as to what it wants to be again. And the reason the neutrino can kind of be this ball of probability is because it interacts via the weak force. Because it interacts so rarely, it's as if it can't notice the universe around it. And so it acts like this quantum mechanical thing instead of being definite and determined all the time. And the reason electrons are definite and determined all the time is because of this electromagnetic force, it being infinite in range, and it's always going to come into contact with some electromagnetic force. It's always going to be reminded constantly that it's an electron, and therefore that it has a certain charge, a certain mass, and certain things like this. Whereas a neutrino has a bit of time to change its personality. And this is the kind of thing that we're looking at, because we're trying to understand trying to understand exactly the characteristics of a neutrino. And the reason we're trying to do this is because we believe that in the very early universe, there was a slight imbalance between matter and antimatter. Okay, when I talk about antimatter, so matter is all the normal stuff around us. The visible universe is constructed from it. And we know that something called antimatter exists, and it's a total mirror opposite. So when I say mirror opposite, I mean it interacts with these forces in entirely the opposite way. So where you've got an electron which has what we traditionally say is a negative electric charge, you have an anti-electron with a positive electric charge, which we call the positron, and vice versa. You can for every one of these 12 building blocks I've been talking about, you've got 12 antimatter building blocks as well. And we know this works because we turn vast amounts of energy from our particle accelerators into new mass, into new particles. And what we find is they create equal amounts of this matter and antimatter. And now that's a problem because opposites always attract, and when these things meet, they form just pure energy again. So we believe the universe was created from a pure energy Big Bang. There was this creation of mass from energy, and then there's a little imbalance between the matter and antimatter, which left over a load of residue matter. So this imbalance is something that it's kind of the holy grail of particle physics at the moment. And in fact, there's one experiment on the Large Hadron Collider called LHCb, which is looking for this imbalance, not within neutrinos, but is looking for it within things called quarks. They're the things that make up protons and neutrons and other heavier kind of mesons that we call them. But the neutrinos are interesting because there doesn't seem to be enough imbalance with the quarks, and so therefore we've got to look to the other half of the building blocks, and we're talking about the electron, its heavier cousins, but they're tightly knitted in with the neutrinos. And so we need to fully understand the character of the neutrino before we can start looking at the imbalance between them. So this is what I'm doing with my experiment. It all sounds a little weird. Essentially what we're doing is we're recreating nature on a very controlled scale, as a lot of our experiments generally are. So right above you right now, in the sky above Dublin, there's thousands of protons, thousands of charged particles raining down on the upper atmosphere, and they're hitting the atmosphere and producing showers of new particles. Much in the same way, in our accelerators, we turn energy into mass. It's just doing the same by hitting the atmosphere and interacting with the O3 or whatever in the upper atmosphere and raining down new particles upon us. And in those showers, we get lots of neutrinos. And in fact, we've used them to death to try and understand the neutrino. So now what we've done is we've turned nature on its side, and we're instead feeding protons from a particle accelerator into our own man-made targets. We haven't got a jar of ozone, but instead we use graphite, pretty much the same stuff that's in the center of your pencil, producing showers of particles, manipulating them with magnetic fields, because in the end, what we get is neutrinos as an end product. And we're firing them straight through the crust of the Earth. Because 99.999% is empty space to neutrinos, they don't really see the Earth as being there. It's more transparent to them than a piece of glass is to light, so they don't care. We fire them straight through the Earth, and we take a small sample, because we can only get small samples because they interact rarely, and we sample them just after we've created them, and then we sample them in my experiment 300 kilometers later, and we try and measure this character difference. We try and see whether they've decided, we create them as a muon type, and we're interested to see if they've changed their mind and become maybe electron type. And we can do this by seeing what charged particle they produce in our detectors. So this is the real physics goal behind all of these neutrino experiments that you might have heard of in the news, but I know full well that everyone's heard of the faster than light thing that's been going on. Back in October, an experiment was producing neutrinos in exactly the same way as I described, using protons from an accelerator at CERN, not the Large Hadron Collider, but a slightly different one, and firing them just slightly, well, twice the distance, 732-ish kilometers from CERN to a mountain in Italy, Gran Sasso. And they were using a higher energy neutrino, but they were essentially looking for a similar kind of thing. They were looking for muon-type neutrinos actually turning into the heavier tau-type neutrinos. And that's why they were using more energy, because they needed more energy to create the heavier mass taus, if you like. So that's why they were doing that. They have one candidate event for that, but they seem to have found their biggest interest in physics from timing the neutrinos. So it's always important that we know to a great degree of accuracy the distance, and this is because the character change of neutrinos depends on the distance and the energy. It's actually the distance divided by the energy of the neutrino, which gives us how regularly they decide to change their character, because it is kind of like a wave function. And so you need to know the distance and the energy in the neutrinos accurately. And so knowing the distance, you also got to measure the time accurately as well. So they measured a discrepancy of 60 billionths of a second. They were saying that neutrinos were arriving 60 billionths of a second before light should have done. And now that isn't amazingly profound in itself, because I mean, when you were talking about accuracies of billionths of a second, you would have thought, okay, well then surely their errors make up for it. But the profound thing was, they said that their errors were less than 6 times that amount. They were saying it was less than 10 billionths of a second. So what they were saying is, with a confidence of over 6 times their errors, they were seeing these neutrinos traveling faster than light. And that was the important bit, is that they were saying that they looked over their experiment and said that the errors were. But at the same time, they had to say, we could have got something wrong. We could have missed something in our experimental setup. We're not sure. And in fact, just a month and a bit ago, they mentioned it could be down to a loose optical connection on one of their GPS units. It's fine. I mean, when you're talking about an experiment like this, I mean, I've very much glazed over the complexities, honestly. When you're talking about experiments like this, you're basing it over hundreds of kilometers, and you're using everything from a particle accelerator right through to, up to 10 or 12 different technologies to try and see these things. there might be an odd loose cable here and there. And so another experiment, which is based actually in the same Gran Sasso mountain as the Opera experiment, they use a slightly different detector technology, and which obviously gives them a totally different kind of setup in their experiment, but they're using the same neutrinos sent from the same beam. And what they managed to say with just looking and seeing 7 neutrinos, which still took them a good couple of months to do, because they're so rarely seen, they were able to time them to enough accuracy to be able to say, okay, well, we've measured the neutrinos coming from the same beam line using a different setup, but still as accurate as the Opera setup, and we see that it's totally consistent with the speed of light. This experiment was called Icarus. They actually published last week, and they mentioned this in a paper which is submitted to the archive, so they're in contradiction with the Opera experiment already. How am I doing for time, actually?
You're fine.
Okay, so they're in contradiction with the Opera experiment, and now a lot of people in my field were kind of feeling that it must have been something to do with the experimental setup anyway. Obviously, we would have loved it to have been true, because any amazing leap forward, as an experimental physicist, I want it to come from experiment, because, and it usually does, because you learn from probing nature, but obviously there are developments in theoretical physics. Some of these guys make up brilliant stories, and they can predict amazing new things, but where we are now is we're looking forward to experiment actually proving some new things about science. But back in October, actually, I was really skeptical when I first heard this, and the first thing that sprung to my mind was supernova. So do people know what supernova are? So they're explosive death of stars that are around about and over 5 times greater the size of our sun. And in a death of a star that size, you get a collapse of the very core. So these stars will burn and fuse atoms together until they form iron. When they can no longer fuse these atoms together, because iron's the most stable element you can get, basically, then the radiation stops emitting and gravity starts winning. And as soon as that happens, you get a massive implosion followed by an explosion. And for a brief moment, this can become one of the brightest things in the night sky if you're lucky enough to see one. And the supernova I was thinking of was 1987A. Now, I was only small at the time. I obviously can't remember this firsthand, but it's interesting because not only did we see it in the night sky through light, but we also saw it in some of the first neutrino detectors that were out there. Now, this is very interesting because, let me get this right now. I'm going to try not to look at my numbers. It's about 170,000 light years away, 167,000 light years away, that this supernova went off. Plus or minus 10,000 light years. There's some astronomer errors for you. And so this was a whacking distance away. And if you think about how rarely neutrinos interact, the detectors that were around at the time, there were 3. Kamiokande, which is based in Japan, where actually one of my detectors is based for my experiment. There was a detector in the US called IMB, and there was a detector in the Soviet Union called Baksan as well. The one in the US and Japan used the same technology, but the Russian experiment, Soviet experiment, used a separate, different technology. In Japan, they usually saw maybe 1 neutrino a day, and this was coming from the hundreds of billions every single second that are flowing from the sun, but also those coming from the atmosphere that I was talking about as well. They saw maybe 1 a day. In the experiment in the US, it averaged out at about half a neutrino a day. In the one in Russia, they got considerably less than half a neutrino a day, maybe about 1/4 to 1/3 of a neutrino a day. And when this supernova went off, the experiment in Japan saw 13 neutrinos. The one in Russia saw 8. And the one in the US saw 8, and the one in Russia saw 5. That wasn't in a day, that was in 13 seconds. So in 13 seconds, they had kind of gone 12 times their usual numbers in what they'd see in a day. Okay, so if you think about that, I mean, I'm just trying to give you some scale of the flux here. It's a huge amount. And the reason behind this is that bright supernova in the night sky, the light coming from it is around about 0.1% of the entire energy, or 0.01% of the entire energy coming from that explosive death of the star. So even though it's one of the brightest things in the night sky, it's only a small amount of the energy coming from it. In fact, 99% is coming from neutrinos. Okay, so I mean, if we could see neutrinos, we would be absolutely blinded. I mean, and if neutrinos interacted like light does, then it probably sterilise the entire Earth. Just to give you an idea, I think it's kind of times 10 to the 50 the flux of neutrinos that's coming from the sun every second. That kind of amazing amount. And so this was very interesting. And then I thought about this, and I thought about, okay, well then, we know the time of the neutrinos, we know the time of when we saw it in the night sky. If we do take the opera result, how many years, how much time before the light should we have seen the neutrinos? And it turns out to be 4 years, just over 4 years, and carrying the errors, that's plus or minus 1 year. Okay, mainly because of the astronomer errors. But but if you then think about that, not all 3 experiments were active 4 years prior, but the one in the US and the one in Japan were. And considering they were the most sensitive anyway, we can look back in the data historically, and we saw no evidence of neutrinos or any anomaly in the flux of neutrinos then. They were seeing their usual regular 1 a day or half a day. And they actually did arrive a little bit before the light, I will be honest with you. They arrived roughly 3 hours before the light. But that was expected from the theoretical models because the light was kind of held back from being able to reach us. And this is because light, as I said, is the carrier of this electromagnetic force. And what you've got in this explosion is you've got a lot of charged particles, got a lot of kind of plasma. And so the light that's trying to escape is held back through interactions with these charged particles. But the neutrinos, because they don't really interact and everything around them is pretty empty, they were able to flow, and so they got a bit of a head start. And so the neutrinos seem to be were consistent with the speed of light from this experiment. And there are other reasons as well, which I'm happy to talk about as to the consistency. But when you think about it, there's so much science backing up, so much evidence backing up the fact that you can't break the speed limit of light. That we had to think it was some kind of experimental error, and it's turning out to be that. An opera itself, with its cable plugged in, will be able to tell us what their experimental setup is actually seeing in May. So look out for that. My experiment in Japan is again producing another independent measurement. We're timing our neutrinos a lot more accurately now because we feel we have to. And there's also an experiment in the US, because we didn't need to before for the characteristic change. It was just now that we're racing them. And there's an experiment in the US as well, which is also going to try and reproduce the results. So I guess it's watch this space, but with neutrinos it will take a little bit of time. So thank you very much. I guess that's about it.
Another sort of 10 minutes before we get food. Does anybody have any questions for Ben?
Sorry, I do speak quite quickly.
Yeah.
Sorry, you have a stupid question, but as you said, neutrinos through the weak force interact with electrons and stuff. Do they have the potential of changing electrons to muons to tau back again by getting released by the muon or tau?
So neutrinos, when they interact via the weak force, they cease being kind of probability, and they have to make a decision there and then. And so when they interact, they're definitely muon-like, electron-like, muon-like, or tau-like. And so when they interact, they produce definitely one of them. The only way that they can change electron like this into muon likeness is through this change of characteristic over distance. and it's something called oscillation, and that is the only way that you can change your electron lightness into neon lightness, and violates, if you like, how electron light, mu like, or tau like.
Reverse, going backwards?
Well, it's an oscillation. It's an oscillatory pattern. So if you leave it enough distance, it will go back again, and it will go back and forth, back and forth. And if you had a perfectly collimated neutrino beam, then yeah, you could probably stick detectors along the entire path, and you'd see this oscillatory pattern. And this is used actually with things like nuclear reactors, because the detectors themselves aren't at different distances. It's the sources that are at different distances, so they can actually see this oscillatory pattern forming. So. Yes, sir.
How can you tell that the neutrino you're seeing either at the other end of this long path or at bits in the middle is the same neutrino?
Okay, so this is where we've got to manipulate in nature. And what we do is, obviously there's a constant stream of neutrinos coming from the atmosphere, but we send small packets, billionths of a second packets, like 10 billionths of a second, so kind of bullet-sized packets. And then we use GPS systems to tell our detectors when to expect them. And we obviously don't tell them just such a small window. We do open the window up. And we can calculate, the background that we get from, false non-neutrino things coming in, and we fold them into the errors as well. But because they're so short and sharp, we can tell they're ours.
You're only getting a small proportion of the neutrinos that are generated.
Yes.
And you're only getting a small proportion of neutrinos that you got at the beginning, at the end.
Yes.
So you're getting tiny, tiny proportions.
And extremely tiny proportions. I mean, to give you an idea, our near detector measures, so the detector that's just 300 meters away from where we create them gets hundreds of events a day, which is amazing for neutrino physics. Whereas our far detector has maybe got 7 in the past month and a half. So, and that's a little bit of the fact that we can't produce a perfect kind of laser beam of neutrinos. But also because of the fact that they are changing.
Yeah.
So.
When you're generating, are they all the same sort?
99% muon-like type neutrinos. So we expect a small contamination of the electron type, and we account for that. So. Sorry.
Yep. With these neutrinos passing through matter, through bodies, through space, is it the change in the characteristic that you're detecting, or how do the detectors work?
So they work just through this weak force principle. So the only way we can infer that a neutrino has interacted in the detector is by seeing a charged particle. That's the only way you can do particle physics, is if see something directly, if you like, if something has a charge. And so you have nothing coming in, and then suddenly these charged particles, the electrons or heavier versions, are being born from nothing, and they're being born from nothing with no other charged particles around them. So they had to have come through this process from the weak force, and so that's how we see them, and that's why it is so rare, because they have to hit that 0.01% smack on. So. At the back there, sorry.
This one thing, the neutrino, does it stop? When it hits something, is that the end of it, or does it keep on going?
It depends in terms of how via the weak force it interacts. One way it dies, another way it exchanges what's a heavier version of a photon, essentially. So in one way it will scatter, giving off one of these heavier versions of photons. Another way it will literally morph itself into a charged particle, so give up its life to produce the charged particle directly, and in doing so it exchanges another force carrier with the nucleus. So. And yes, sorry, Mr. Gentleman.
Just a quick question. You mentioned about the experiment in which you said that the light was held back. Someone was obviously holding the light back from when the neutrino obviously reached 3 hours before.
Yeah.
Was the I think the light, I'm not too well up, but the speed of light is a standard measurement. Was the neutrino going faster than that standard measurement?
No, the neutrino was travelling pretty much near the speed of light, because but the light was bouncing about, if you like, between all the charged particles, because it was being affected by electrons and protons and things that were being expelled in the explosion. So light was going through a treacle essentially, and being slowed down. So it was traveling at the speed of light, but it was kind of taking a meandering path, if you like.
What sort of applications does the research have in the industry? What sort of interest is the kind of research you're doing?
What for the neutrinos? So again, actually, last week, a group of neutrino physicists decided to send a message in neutrinos from somewhere in Chicago over to some mine in Dakota, and they sent the word neutrino in 7-bit ASCII, and they had something like a 99% data accuracy, which I've been told is very poor for information theory, and that was, I mean, it's kind of interesting. It was a nice idea, because for a long time people have always said, well, if we ever get to travel to different stars, interstellar travel, then we probably wouldn't want to use electromagnetic communication, so light or radio or other forms of electromagnetic like that, because there's so many magnetic fields and charged particles out there in between, your source and your destination, that it will get deflected and your signal will be attenuated. It'll get weaker as it goes. Whereas neutrinos, because they don't interact, you can send them direct, and they fly straight and true. So someone took this whole sci-fi idea of interstellar communication and decided to try and prove it on the Earth. So there's that kind of application, and there's also research into using really intense neutrino beams to essentially diffuse nuclear bombs, because it can stop because a nuclear bomb is just a runaway weak force chain reaction. If you can use neutrinos to essentially douse the fire. So there is research into that as well, but you need a massive intensity of neutrinos. So, and apart from that, there's lots of spin-offs as well from the technology. Some of the technology we're using in our detectors is being used now to make medical imaging a hell of a lot cheaper, and other bits and pieces like this. So.
Anybody else have questions?
Yes, sir?
You're going to hate this. This is faster than light neutrino stuff.
Yeah, go for it.
But when this all broke, I was in Australia at the time. I'm a physicist myself, and I saw him come into the room gloating at Einstein was wrong, which I'm sure you've heard it.
Yeah, too many times.
In fact, your blog was one of the very first sources that I was able to kind of go, well, look, temper yourself a little bit. But there was a debate with some of the higher profile physicists about, was it ethical for the opera team to release their results the way they did?
Yeah.
Now, I would have argued that it was. That's the idea of science. Look, I can't explain this result. Can someone else possibly interpret it? But there is prominent figures in even the particle physics community that said opera messed up on how they approached it. How it was leaked to the press first. We all know that now in retrospect.
Yeah.
But do you have any opinions on what opera should have done? That experiment, should they have gone the way they did, or should they have bit their lip a little while longer?
I think their hands were tied. Once you say as it was leaked, they really couldn't do it. They had to publish in a timely fashion, because there were enough rumours and stories flying around already. They needed to show the science they'd done, and they needed to be honest, and they were. They were open and honest from square one. They held their hands up and said, "This is where we're at. This is the result we have. Please help us." They opened it up to the community, and so I think their hands were tied through this leak. I'm not enjoying this whole. This leaking way of information getting out. It's happened with the Higgs as well, and things like this in certain cases. I think it should be left to the collaboration to publish in a timely manner once they've had well and good enough time to go through absolutely everything in a fine-tooth comb. But I think their hands were tied in this, because it did just become so big. They had to be honest.
It's probably a bigger question about why there's a policy in CERN of these leaks, because that's not the first time that happened as well.
No, exactly.
Experiments, stuff like you said.
Yeah.
The 3 sigma result, even at Christmas, wasn't supposed to come out. Only that.
Yeah.
There's HiggsRumors.com was going on about it. So.
Exactly, and it's difficult when you've got thousands of scientists working on these experiments. It's difficult sometimes, and some scientists like to get their name in the media as well. So that kind of happens. But in a way it was kind of good, but in a way it was bad, because then when the whole loose cable thing came out, everyone was like, "Oh, come on!" They were just, they've basically just had us put in our leg for the entire time, and it was just a whole media stunt or whatever. But
do you think though that's largely down to that people don't understand? Like a loose cable is not just like a loose cable around the back of a PC.
No,
So,
exactly.
Like, it's several miles down,
Yes.
like with a load of other cables. Like it's
Exactly, yeah. I think well, as I say, the complexity of the experiment and everything, and it was literally just plugging it back in. It was, I think, but then obviously they have to repeat their measurements, which takes them months then with neutrinos. So, but yeah, I think maybe the complexity of these experiments is sometimes lost. I think, because people think, oh, they're just timing something, but we're timing something to very high accuracy and stuff. So.
Can I just add to that? When you're using the GPS, loose GPS connection, GPS seems fairly rudimentary way of actually measuring something as technologically advanced than neutrino. What about looking for light emissions, looking for emissions, other sorts of emissions? GPS seems a little bit.
So,
or maybe I'm thinking just in terms of GPS in normal context, maybe. But
so the GPS we're using is not your bog standard GPS in your phone or sat nav. It's linked to so they're linked to atomic clocks to get the timing as accurate as possible. And there's even atomic clocks which they take from one site to the other to calibrate the clocks and make sure they're synced up nicely. And again, there's multiple GPS measurements taken at different locations to try and get the distance right. They've got so many different redundancies in the different systems that they can cross-check in so many different ways and reduce the errors and make it a hell of a lot more accurate. So,
does it look also that if one GPS was out and the rest are all in sync, does it still mean that it's probably more likely that it would hold true that the neutrino was?
So, but the thing is, as long as you know that it's out, you can adjust for it. The important thing with these experiments are the errors, as I was saying earlier. It's not the result as it was. It was the errors being so much smaller than the result. So it's all about the errors. And in fact, they got an offset of about 1 microsecond, so 1/1,000,000th of a second originally. So, but they knew for a fact that neutrinos weren't traveling that much faster than light. Because they had delays in all their different electronics, all these different clocks, and these different redundancies in the GPS that they had. But even when they took away the redundancies that the times that they'd measured, they had this residue of 60 nanoseconds. And as I say, it's the error on it that's important. So.
Anything else? Any other questions?
Yes, sure.
Do you ever get really frustrated when you've read a paper that's completely logical and useful, and then you read something in the Daily Mail like, oh my god, scientists are totes lying about the speed of light? Do you ever just want to throw things heavier than neutrinos?
First off, I try not to read the Daily Mail. That's my first port of call. It does frustrate me a lot, and it does make me a little adverse to reading popular media. But I mean, just to give you another example of that is not necessarily that they blow it out of all proportion, but sometimes they just kind of get it just a little wrong. I mean, the Icarus experiment published results I think 2 weeks after the Opera experiment did, and they stated a theory paper and said our experiment contradicts this theory paper, so therefore the Opera experiment is incorrect because it states that neutrinos aren't traveling fast in the speed of light. But that same theory paper contradicts Opera's own results itself. And it was just a case of that the Opera experiment, so this Icarus experiment, when they published that, hadn't brought anything new to the table. Yet, because it was in the media, because it was in the line, it's like, now this experiment says it's wrong straight away, when it really didn't add anything to the argument. So sometimes it's a little bit of both, but I do get annoyed at it all, I have to say, but I don't like to say it sometimes. I think that's as much as sometimes the scientists as it is in the media. It's like maybe we don't communicate our science well enough, so I don't know. See.
What are the implications if it turns out to be correct?
Massive, as I say. So this quantum mechanics I'm talking about, and the theory of theory of everything on the largest scales, general relativity, they're both reliant on this upper speed limit. So quantum mechanics is built on special relativity, and and the largest is built on general relativity. Even though they don't agree, they both agree that there's this upper limit needed in their theories to make them work. And so it would mean a total rethink. And this is why it was kind of exciting, because if it meant a total rethink, maybe it was hinting at something that was maybe marrying the two together. But you know, I think the Alpha experiment is going to prove that it's totally consistent with the speed of light. Yeah.
Do you want to go ahead with your question?
Yeah, hi. Is it true to say that supernovas are a calibration unit in cosmology and astrophysics? Would that be correct? Yeah.
I don't think I'm qualified to say that.
I'm just thinking if neutrinos are arriving at an indeterminate time ahead of actual light photons,
okay.
do they become sort of does the supernova become sort of busted flush in terms of?
I know there's astronomers or astrophysicists in the audience, so they might correct me if I'm wrong. But the theoretical models of supernova were not working. They were trying to figure out why the supernova that they were creating in their computers were not exploding with this infall of matter. They just couldn't get this explosive bounce back. But it was found if you add this massive amount of neutrinos, you could get this bounce back explosion that you expect from the supernova. So I know there is a little discrepancy as to how well we know the supernova and how well we know the neutrinos from the distance. And so they're not standard candles by any long shot. That's still unknown. That's a physical thing.
I just think now actually, but going back to your the scientists maybe need to communicate more. Do you think that there's a need for sort of a Friends of Science kind of outreach program, or I know that in Australia at the moment there's Friends of Science in Medicine, which is doing an awful lot of work to get rid of homeopathy being taught in universities and stuff like that. So I'm just wondering if maybe there needs to be kind of maybe some scientists are not particularly good at explaining their work, so maybe there needs to be an interim sort of an intermediary.
Is that why we have journals?
Yeah, but not everybody
Daily Mail.
That would be an interesting an interesting intermediary, but I wouldn't know. I wouldn't like to think about how it would work, but yeah, it would be a good maybe. I think a lot of the fact, talking from science point of view, is certainly in my field. It's a difficult field to try and get across, and I think I've proven that tonight with how badly I explain some things. But it's because of that. There's that extra level of I'm not trying to explain this to school kids, but I think we need to, within our own community, maybe encourage and promote outreach and science communication a little more. And I'm doing that amongst my colleagues now. I'm roping them into it. So. Sorry, I think this gentleman was next there. Sorry.
So I'm just going to go back to basics.
Okay.
Really bad. You're saying in controlled environments that you guys create the neutrinos, and they're generally muon neutrinos. Now, when they change their personality, do they all change at once, or is it a complete random, disorganized change where you say 5% change to the tau, and 5% later change to the neutrons? Okay, well. As I mentioned, it's a probability, so they stop being definite objects like snooker balls or something like that, and they start to be just a fuzz of pretty much all the different possibilities, so all the three different types at once. And then it's not until they decide to interact with the universe that they have to make a decision. And in that decision, again, they'll have different probabilities as to which one they'll choose, as to which one they'll essentially collapse into. And because you can only measure one neutrino at a time, you have to take thousands of photos to try and get an idea of the picture of the probability, because you can't get it on a individual basis. So we take thousands of them to see what the probability is.
Okay. We'll take one more question, that's all right.
Yeah?
And I think we'll take a break then. It's probably getting a little bit warmer here.
Yes.
Sorry to go back
Yeah.
to but do you think a lot of the misconceptions about that arise from the hero worship of Einstein? They put Einstein up there on a pedestal, but most physicists will tell you that after 1930s, most of Einstein's output was pretty terrible, scientific error, like cosmological constant and all that. but we still, in popular culture, we use the word Einstein to, and it's like he arbitrarily came up with these speed limits. He discovered them, but he didn't. They're part of the universal fabric. And I think, this is my just observation, I think when all the headlines are saying Einstein is wrong, whereas maybe they should have said this theory may have problems in the ground. Is that a problem that people don't want to understand it? They want to personalize it to one individual rather than the entire background?
I think that helped the media explosion take off, because I think if you can get the word Einstein in there, then that's going to grab a lot of attention. And saying he's wrong is just going to grab you even more, I think. So I think that's probably the reason it exploded so much. But and yeah, Einstein is kind of, you know, personally credited with a lot of the theory which he knitted together, but obviously, you know, things like an upper speed limit in the universe, it's not necessarily his idea in the first place, but he knitted it all together and made it work. So I think it is maybe the media using Einstein's name to get more people interested in science, and I don't mind if it gets people talking about physics, then it's all good. So.
Guys, we take a little break. Is that okay? We want to refill the drink.